We're going to talk about questions about polynomial long division. So raise your hand and let's get these questions out into the open. Polynomial long division, PLD. Nate.
What do you do after you divide the leading by the leading? I really didn't understand that process.
Okay. Got it. Next question, yeah.
Is it possible that you like give us a worksheet that has us like identify the terms so we can get better use of them?
Which terms?
Like the terms that you said in the video that no. Like
So you want to practice long division?
Uh,
Something like that?
You know about like all the terms so far?
no, I'm talking about like how in the video you started.
Dividend, quotient, divisor.
That.
Yeah. 4 words. Watch the video a few times. I can also type them out for you. Yes.
You're probably get to this, but,
yeah.
How we use it in...
What's the point? Yes. Yes.
I'm sure you're going to answer this tonight.
I hope so.
What are the oblique and horizontal asymptotes, and what do they tell us?
What are HA, OA? Other questions? Other questions? Anything else? Yeah.
Like, can this like technique be used on like higher powers?
Does this technique extend to higher powered polynomials?
That's a good one.
I like that. It's good. Any others?
Go over to like the beginning of it.
Okay, here we go. So, what do you do after you divide the leading by the leading? So let's just do the beginning one. Let's just do the beginning piece of one. Let's say you had x plus 1, and you're going it into, just like long division, how about, I don't know, 4x cubed minus 2x squared plus x plus 17. Leading means first, the leading term. Can you hit the lights again, Hammer? Actually, I think you guys like it. It's better when it's off, right?
Yeah, totally.
Yeah, it's fine. Solnit, file work later. Pay attention now. Thank you. What are the two leading terms?
X plus 1 and...
Terms.
Oh, X.
Leading and leading. This one always stays the same. It's always static. But now we have 4x cubed over. So what's that equal?
4x squared.
So you put that over the 4x squared, and now you multiply it by this term, just like you would in regular long division. And you end up with 4x cubed plus
4x.
And now you subtract. Put those parentheses around. I can guarantee you're going to spend the next 2 to 5% of your life, for the next week or so, backtracking because you forgot a minus sign. You'll be very sad. What do you end up with?
You end up with negative 6
X squared. And now you just do the exact same thing again. Bring down the x, and you do the exact same thing again. We're not going to finish this one. We're going to do we're going to do a bunch of examples today. But that's what you do with the leading over leading. And then what do you do next? Same thing. You keep on repeating.
If you put down the 70 right away, it doesn't change anything.
Not really, no. It's there. It's just for notation. Yes?
If divisor is a higher power than dividend.
Nah, not doing that. You will not be doing polynomial long division.
But does the process change how much?
No, it's a one step. You're done. Okay, is it possible to get a worksheet? Yes. What's the point? I don't know why it's tabbing in that far, but what's the point? Polynomial long division will tell us about the oblique asymptotes. Exciting. Nope. What are horizontal? HA means? And OA equals oblique. What does oblique mean? Slanted, tilted, not horizontal, not vertical. Does this technique extend to higher ordered polynomials? Yep. The big punchline to all of this is everything we're learning now can be extended to
Everything else?
everything else. Exactly. Okay, so let me pause for 1 sec. If we wanted to play around with this, let me go back here. We could arrange to maybe look at it in a different way. Might tell us something interesting about the function or useful. Another way to write that division is this. Let's run that division. See what happens. 3x squared is the first leading over what? X. And that x is going to stay the same, so it turns into 3x. 3x times x is? Subtract. What do you get? Minus 6. So it turns into 5x over x is plus 5. So you get 5x minus, and you subtract, and what do you end up with? What?
Negative 1.
See, there's 1% of our class gone. And that is the remainder. So yes, what are these called? The 3x plus 5 is called the quotients. The x minus 1 is called the divisor. And this is called the dividend. And the negative 1 is called the remainder.
Can you write that now?
Yes, sure. So what did we just do? We just did one thing. We took 3x squared plus 2x minus 6 over x minus 1, and we now know that that's the same thing as 3x plus 5 plus what?
Negative 1 over x.
Yes,
Minus
that is correct. That's what it is. How would you verify that?
1. Multiply.
You'd multiply 3x plus 5 plus negative 1 over x minus 1. What would you multiply it by? X minus 1. And you do that one at a time. You turn it into 3 times x minus 1 plus, 3x, sorry. 3x times x minus 1, 5 times x minus 1, and minus 1 because it kicks the denominator out of there. And you're left with 3x squared minus 3x plus 5x minus 5 minus 1. And we have 3x squared plus 2x minus 6, which is, what's that term called? The dividend. What did we just do here? I explained this in the video. We took the, what is this? That's the quotient plus the, what's that? Remainder over the divisor times the divisor. And that turns out to be, this right here is the quotient times the divisor, and this is the remainder. So, and that must equal the dividend. Yes. That's long division. How many people did that in grade school? Yay! Anybody do square roots by hand? Anybody? Up until calculators were commonly used in classrooms, in grade school you learned how to do square roots by hand. And the mechanism, it looks very similar to long division.
Is it the box with the...
No. Well, there is that method too, but there's a method that it looks, if I just wrote it down and you looked at it from afar, you'd be, oh, it's long division. It's not doing long division. You know what it's doing? Finding the square root to an arbitrary... You know how square roots, a lot of them are irrational? Like if you did the square root of 7, it's irrational, goes on forever, no pattern. You can keep on doing this method as long as you want, and you can make it as accurate as you want. It's pretty neat. Yeah, you could look that up if you want to.
We did one where we just
Square roots by hand. Look up the method. It's pretty neat if you want to. I think it's pretty cool. Okay, so you ready to do a little bit of graphing? You actually want to put it all together into something fun? Let me pick the right equation. I'll copy it out. Let's talk about, let's talk about that one, so that's fine. So, we took this and we ended up with this. Let's give it a name. What letter do we want to use? H? Sure. Do you like H? H? I think H is good. That's fine. So we have h of x is equal to this. And what did we do? We just figured out how to rewrite it a little differently. We need to examine end behavior. End behavior is what happens when x gets really, really big positive or really, really big negative. We're going to look at those two things. So, what happens? We're going to look at this form. The reason we use polynomial long division to get that form of what we started with. What happens to 3x? What happens to 3x as x gets really big? What happens to 5 as x gets really big? What happens to negative 1 over x minus 1 as x gets huge? As x goes to infinity, what happens to 5? Really? There's no x in it. It stays the same. What happens to 3x? It gets bigger. It's always going to be 3 times whatever the number is, correct? What happens to this as x gets huge? Smaller and smaller and smaller. What does it go to? Gets infinitely close to? 0. It gets infinitely close to 0. The big kid language of this, everybody, is as follows. H of x, the limit as x goes to infinity of h of x is going to be, what do you think it's going to be? Take a look at this. As x gets huge, what does it go to?
Almost 0 to infinity.
Well, this goes to 0, but the other two parts go to 3x and 5. As x gets bigger and bigger, this becomes less consequential. As x gets bigger and bigger, this whole thing gets closer and closer to what? 3x plus 5. As x gets huge, the function looks more and more like what? 3x plus 5. As x gets bigger and bigger, this function looks more and more like 3x plus 5. Why? Because this term right here becomes less and less important. What happens as x gets bigger? What happens to this term? It gets closer and closer to 0. But this always stays 5, and this always stays 3 times the value you're plugging in. But as x gets bigger on this last term, it goes to 0. Okay. So, what is this? What did we just find? What do you think we just found? An oblique asymptote. Yes, we just found an oblique asymptote. And it's not vertical, exactly. Let's make something up. How about f of x is equal to x squared plus 2x minus 3 over x minus 4. Let's take a look at this one. Let's see what we can figure out. What do we like to do first? If we're going to do the full analysis, what do we like to do first? We love to factor. Simplify if we can, sure. What's the factor form of the numerator? Someone raise their hand and just tell me what it is. Gare. Try again. I liked your vigor. Good. I like the confidence. That was good. Just go for it. It's kind of like the kid up there, 7 times 5 is 75. Why? Because I feel that way. I think we should have a feel that way math class. Everybody gets up and leaves. No, you can't do that. So, can you please, someone who hasn't spoken, tell me what's the domain of this function? Danilo.
Well, it can be 4.
So what's the domain?
It's x such as x plus 4.
Yes. And you can use this. You like that other set notation, Danilo? That's fine. You can use it if you want to. Intercepts. Can someone tell me the y-intercept when x is 0? What's y? 3 over 4. And what are the two numbers that make y 0? Negative 3 and? We have 3 points. That's pretty good. What about symmetry? You can just shout this out. What do you think? Not. Neither. There might be some cool symmetry. When these are 0, that goes away, that goes away, that goes away, and you have... yes. Look at the unfactored form.
But even if you look at the factored form...
It's 3 times negative 1 over negative 4. You should. This is generally easier to look at, though, because the constant's already out there. Okay, so let's move into funland. What about the vertical asymptote? Hannah, what is it? X equals?
Oh my gosh.
Stop looking at the notes.
The 4 and...
Yep, 4. Good. Stop. Not and anything else. What's the only thing you can't plug into the denominator after it's fully simplified? 4. Is there a removable discontinuity? None, because nothing canceled out of the numerator and denominator. Now let's go to oblique land. Oblique land. We need to rearrange this. We need to rearrange. How are we going to rearrange it? What's the key? PL what? D. Polynomial long. And the reason we're going to do this is it's not evenly divisible. So let's divide. What are the two leading terms? X squared and x. So it's going to be x squared over x, which is, so we have x. X times x is x times a negative 4x. When we subtract, what do we get? 6x minus 3. So now we have 6x over x is 6. 6x minus 24. You subtract and you end up with 21. 21. So again, everybody, what's that called? Quotient. What's this called? Dividend. Dividend. And what's that? Divisor, and this is the remainder. So we just showed that our original fraction, x squared plus 2x minus 3 over x minus 4, we just showed that that's equal to x plus 6 plus what?
21 over x plus 4.
Yes, exactly. Now, what did I give this a name? Did I give it a function name? G of x, I think? F of x. F of x. The original function, I called it f of x. I'm just trying to be consistent with the notes. So we want to know this. The limit as x goes to infinity of f of x. What happens when x goes to infinity on this thing? What does this go to?
X plus 6.
X plus 6, exactly. We just found out a horizontal asymptote. We have intercepts. We have a lot of information. Let's put it together. So let's put what we have together so far. Let's put what we have together. Here's what we have, everybody. We have one intercept at 1. We have one intercept at, and we have one intercept at 3/4. We have a vertical asymptote at x equals what? 4, right? And then we have an oblique asymptote at x plus 6. And I'm not going to do this to scale, but it looks... I'm going to call that 6, okay? It's really okay if you warp it for now. So, we put in some dotted lines. Let's go with what we know. Does this graph cross anywhere else? Does it cross the axis anywhere else except at these 3 places? No, it does not. So, let's just connect dots. That's that part. What was the first thing we found out about this function? We found out that the domain of this function was everything except for 4. Exactly. It was everything except for 4. So are we done graphing this? No, we've only covered everything to the left of... We've only covered everything to the left of 4. So we need to go to the right. So here's where I give you a little bit of investigation power. We're going to look at the original factored form. What's the power of x minus 4 right there? Nope. Power is 1, which is odd, which means different directions for asymptotes, for the pointing on each side. So here, since this is odd, that vertical asymptote, you can call it, it's an odd, it's called a multiplicity. Just remember that. The power of x minus 4. The exponent is to the first power. So we go back here. So if it means odd multiplicity, it goes in different directions. If this side goes down, the other side has to go up. So this side, you know it has to go up like this. And what do you guess the rest looks like?
Curves up.
It's going to curve up towards this, which is y equals x plus 6.
And you never crosses y.
We're going to talk about that in a second. All we know it doesn't cross right now is it definitely doesn't cross the vertical asymptote, and it definitely doesn't cross the x-axis or y-axis anywhere else except for those 3 points. That's all we know for certain right now. Let's check and see how this meshes with reality. That is the graph of our function. And what else did I graph there? X plus 6 for just for visualization purposes. Does that match what we got? Yeah, it matches pretty well. It matches pretty well. Now here's the thing. Am I too concerned with scale? Not really. You have to be careful. Sometimes you're going to graph this and your window is going to be right here and you're going to be like, oh my god, I didn't graph it right. You need... I'm serious, that'll happen, especially with these, because these graphs can look really weird. We had to play around for a little bit to get this graph. This right here, what is this line? Is that actually on the graph?
No, that's good.
Oblique asymptote. Well, and then what's right here? X equals 4. And if you had to graph this by hand, the only things I'm really interested in, what we're labeling already, the intercepts, like that. So, now that we've found one oblique asymptote, what's missing? What haven't I told you about? Horizontal.
So it doesn't really matter if like you don't have any points for the top part. It doesn't really matter exactly how it's
In this case.
Exactly. If you wanted to, what could you do, Felicia? Exactly. Sometimes you're not going to quite have enough information, and you're just going to have to pick a value and plot it. Like sometimes you're going to be stuck. Usually it's a logic kind of domino effect. You're going to plot here, and you go, oh, it goes this way. It must go like this. It must go like this, and then you're done. Sometimes, though, you're not going to know if it's above or below that line, and what are you going to do? Pick a value out. Pick a value like right there, and you plot the point, and it ends up right there. So you know it has to be on that side. So what about what about horizontal asymptotes? And this is what I want to give you. Let's say I gave you a new function, 4x to the 9th plus 2x squared plus pi over 7x to the 9th plus x minus e. I'm just making it look fun. If I look at this thing right here as a whole, and I think about what happens as x gets huge, if I think about what happens as x gets huge, looking at the numerator, what's the only term that's going to be really, really important as x gets huge? On the top, which term is going to be the most influential when x gets big?
Pi.
Pi? Pi doesn't change size. That's going to be the least one. That's going to be the least. 4x to the 9th. Because by far it'll be so much bigger than everything else. What about just the bottom? What's the big part? 7x to the 9th. So if you're examining the limit as x goes to infinity of f of x, the only thing that really matters is 4x to the 9th over what cancels? What did we just find? Nope.
Horizontal.
And it's horizontal, so what's the equation?
No, y equals 4.
Yep. You just found your first horizontal asymptote. Now listen, everybody. Quiet. Quiet time. Quiet time. Which terms were important? As x gets enormous, which terms are important? 4x to the 9th and 7x to the 9th. What about 2x squared, e, and x? As x gets huge, how important are they? Less and less and less. Think about it. If x is a billion, how big is e compared to a billion? Not much. Not much. The only ones that are going to matter are the leading terms. The leading terms. Here's the summary. That's really important. Given, let's say you had some rational function and it equaled p of x over q of x. If you had these two right here, if the degree of p of x is equal to 1 greater than the degree of q of x, you have a oblique asymptote. If the degree of the top is 1 greater than the degree of the bottom, you have an oblique asymptote. If the degree of p of x is less than or equal to the degree of q of x, what do you have? A horizontal asymptote. Which one did we just do here? What were the degrees there? The degree on top was, they were the same, 9 and 9. So what happens if, let's say I gave you n of x, what happens if I gave you this? 4x to the 12th plus 17 over 16x to the 15th minus x plus 5. What are the only terms that matter as x gets really, really big?
4x to the 12 is 16.
Yeah, the 4x to the 12 over 16x to the 15. What cancels? Well, the 4 does. That's kind of cool. But this cancels too, and what are you left with? 1 over 4x cubed. As x gets enormous, what happens to 1 over 4x cubed? Gets infinitely close to 0. So we say that the limit of n of x as x goes to infinity is, in this case, what is it? 0. What does that mean? Well, what's the degree up here? 12, and this is 15. So it fits this one right here because it's less than. What example did we do up here? This was when the degrees were the same. In this case, though, what is the horizontal asymptote for this function? For this function, what's the horizontal asymptote? Y equals?
1 over 4x. 0.
Yes, because what happens to x as what happens to this value as x gets huge? It gets infinitely close to 0. So what does this graph look like if you zoom really far out? What's it going to look like? Y equals 0. It will look like, what axis is that? X-axis.
So the constants just don't matter?
Not with x to the 15th floating there. The constants only matter if they're in balance, if the powers are in balance. If the powers are in balance, they obliterate each other in what's left, the leading coefficients. But if the degree on the bottom is bigger than the degree on the top, what's the only thing that matters? That degree on the bottom. Yes.
What about the one on the top? What is
Ah, okay. So there's a third case here, right? So in this case, we have this one right here, the oblique asymptote. We have the degree of the top being 1 greater than the degree of the bottom. And then the next case, we have the degree being of the top being less than or equal to the degree of the bottom. So what's the third category? If the degree of p of x is equal to more than what? More than 1 greater than what? Degree of q of x.
So
What happens in that
P is
case?
The numerator.
P is the numerator, yeah. So what happens if the degree of the top is like 15 and the bottom is 4? In terms of horizontal and oblique asymptotes, what do you think? Neither. Neither HA or, in this case, you could technically have a curved asymptote, some sort of curvy line that the thing follows. Do we examine those? No, we don't. Can you have an oblique and a horizontal asymptote on the same graph?
Wasn't that what you just plotted it?
You can't. Wait, we can have a vertical and an oblique. You can have a vertical and a horizontal. Can you have an oblique and a horizontal?
No, because
It's mutually exclusive. You can't have both of those. Can both of these things be true at once? No, you can't. So you either have one oblique or one horizontal or no oblique or horizontal. You can't have both. You can't have both. You definitely can't have both. Kind of.
Oh,
Don't worry about
good
that.
answer.
You can have, I'll just give you this. You can have functions that look like this. In that case, there are technically 2 horizontal asymptotes. That is possible.
Are you going to do those?
No.
No?
Guys, you have enough letters to keep track of. Yes.
What cases? Because the first example you used the result from the
So when do you use polynomial long division? You use polynomial long division when you're dealing with oblique asymptotes. You want to find a linear function. If the difference in degree of the top and bottom is 1, you end up with a linear function. But what happens if the degree on top is 5 and the degree on top is 3? Is that going to be a linear function when you do the division? No, it'll be a quadratic. You'd have a quadratic asymptote. That's certainly possible. Are we concerned with them? No, we're not.
And what's that
So when
practice?
we
We're definitely
see
not.
that kind of rational function, we don't need to bother defining oblique or horizontal. Right?
If you see what?
If we see that
The top is too higher? Yeah. No. You know automatically. Just by looking at the function, can you tell if it has an oblique or horizontal asymptote? Without doing any math? Absolutely. Here's the last little bit of information you need to know. Vertical asymptotes, can you cross them? Exactly. You cannot cross. We have horizontal asymptotes and oblique asymptotes. Can you cross a horizontal asymptote? Yep. Can cross them.
What do you mean by cross?
Actually cross over them. What I mean by that is
okay.
you could have a horizontal asymptote like this,
Yeah.
and the graph could do this. And it would still be defined right there. Definitely can happen. Is that still a function? Yeah, it is. That's why it can cross.
So what you're saying is that just in that direction it becomes
Exactly. These functions look like their end behavior when you zoom way far out, but if we're interested in the interesting parts in the middle, and what goes on in the extreme cases. What about oblique? What do you think? Yep. So the real question is, how do you find out if they cross? It's actually pretty straightforward. Go back to this right here. We graphed. Where's the one we graphed? We graphed this one right here. Who knows? Maybe it crosses there. Maybe it crosses over and comes back. Maybe it crosses over here. Do we know? Let's try and find out.
It can't cross the vertical asymptote.
No, because then it wouldn't be a function.
Okay.
It wouldn't be a
Yeah.
function. These are functions. You can cross it. How many times could it cross the oblique asymptote?
It could.
Remember, how many numbers of answers are there in math? Or infinity. So whenever you have many, it means a lot of them. The really interesting things in math are the ones where you do something seemingly random and you end up with 7 answers. I love math like that, where the natural world pumps out numbers. Anybody read the book Contact by Carl Sagan or see the movie? Does anybody know who Carl Sagan is? I'm honestly going to die a little bit on the inside if no one can tell me at least one thing about Carl Sagan.
He's a scientist.
Okay, I didn't have to die a little bit on the inside. That was good. Okay, part of your homework tonight, I'm just going to do this because I can.
Whoa.
That's part of the homework tonight. Okay, So moving back here, and I will have a tie-in to what we're doing. If I can get Allen Iverson back to Precalculus, I can get Carl Sagan back to Precalculus. Okay?
Still have that video up?
Do I still have that video up? What do you think?
You downloaded it.
Play every game like it's my last.
Okay, you got it? Yes, of course. You know who I am. Okay, so let's go back to this. We looked at this function, right? And we said, does it have an oblique asymptote?
Yes.
Yeah, it does. We might want to know, does it cross it? How do you figure out if two things intersect?
You plug in the value.
No. We don't know the value yet.
You set them equal to each
You
other.
set them equal to each other. So if we have this, and we want to know, does it cross x plus 6, you just set them equal. Let's try this out. No tricks involved here. How do we solve something like this? Step 1?
Yeah, go times both sides by x minus 4.
Yeah, so you end up with x squared plus 2x minus 3 is equal to x plus 6 times. At this point, what do you have to do?
Multiply that.
Yeah, you have to factor it out, multiply it out. X squared plus what? 2x minus 24. What cancels?
X squared and 2x.
What are you left with?
Three.
Negative 3 is equal to negative 24. What does that mean?
There you go.
Frowny face. Assuming you didn't make a math mistake, what does that mean?
They
That
don't
function
intersect.
doesn't work.
Does not intersect. This tells us that you cannot cross. It means that the function never crosses x plus 6. So, we now know, does it cross? No.
And if it did,
And if it did, you could find the value, just like you can find a removable discontinuity. If it crosses, you would end up with, like, instead of negative 3 equals negative 24, you'd end up with, like, x equals 5. And you would know that at x equals 5, the function crosses the oblique asymptote. Ah, tricky. And how do you find the y-coordinate?
you plug it in.
Plug 5 into the oblique asymptote. 1 and then 2.
Okay, so say it did cross.
Yeah.
Could it cross on the like above and below?
Yeah, you can
Like,
have...
How would you find where it crosses above and below?
Well, no, hold on. When you mean above and below, so let's say you had an oblique asymptote like this, and let's say you had a vertical asymptote like that. We knew from other math, for example, in this last question, we knew, I think I understand what you're asking, from our other one, we knew that part of the function looked like this, definitely. And we knew that this had to go down, because it had to go down because that's the only way it could fit. And we knew that, remember, the multiplicity was odd on this thing, so we knew the other side had to go up. So if we knew it crossed right here, let's say that was 5, I'm just making this up, but that's still an asymptote, we know that that had to go up, so what does this have to do? It has to go down, but then
Come back.
asymptotes have really strong gravity. Think about it like that. It can escape for a little while, and then what does it do? Goes back up. You look at other things, and if you're totally lost, what can you always do? Plug in a number.
Oh, also, what about can it cross on the one
Over here?
Yeah.
It could if, for example, sometimes, instead of getting negative 3 equals negative 24, you might get x equals 5, but you also might get 2 answers. It might be a quadratic. So it can intersect more than once. Absolutely. Again, how many times could it intersect?
Infinity.
An infinite number of times. Yes.
Infinity.
Infinity.
It's kind of like a-
That's good. Okay, Nell, yeah. The whole point of it is it describes a behavior of the function. It describes, we now know that as this thing tapers off to infinity, we know what it's going towards. What is it looking like? As you go farther and farther this way, what's it getting closer to? Y equals x plus 6. It tells us more about the shape of the graph, how functions behave. That's what it tells us.
Helps you back.
Yes. Yes, it does. Okay, I'm going to pause for a sec. Oh, I missed all that, but that's okay. So we factored out and we learned that you can use this on any polynomial. If I asked you, though, to find the zeros of this, what would you have to use? This is how I'd like you to write it. Please don't write out the whole quadratic formula to start with. Please do this first. B squared minus 4ac. What's that going to be? Negative 1 in parentheses squared minus 4 times 1 times 1. That equals 1 minus 4, which is?
Imagine.
So it's negative b, so negative 1, plus or minus the square root of negative 3 all over 2 times 1. So if we simplify this a little bit, x is equal to 1 plus or minus I root 3 all over 2. I know you guys don't know what imaginary numbers are, but there you go. So how many zeros does this is a 4th degree?
We'll get there.
It has 4. It's a 4th degree. So how many times could it cross the x-axis? 4 times. How many times does this one cross the x-axis? No, it crosses
Twice.
right there. Look, kids. These two. It crosses there. Are these intersections? No, they're imaginary roots. But how many did we find all 4 roots?
Yes.
Technically we did. Okay. So here's what you're going to work on for homework.
Right?
Yeah, why is he so cool?
He has a theory of his own. Am I right?
He might have had some theories, but why is he cool? Okay, with that, we are... Any last questions before I tell you what's next? Any last questions? Okay, hold on.